Welcome to this lesson about the fundamentals of probability and statistics. In particular, in this lesson, we will deal with the concept of probability and random variables. Let's start with the probability. So, if we consider an experiment with random outcomes, we can define event as the set of the outcomes of the experiment. So, the event occurs if the outcome is one of the elements of the set. We can define probability as PR of something, of an event A, as a measure. This measure must satisfy three axioms of probability. So the first axiom is that probability of A must be greater or equal than 0. The second axiom states that the probability of S, the sure set, is equal to 1. The third axiom is that if the intersection of A and B is equal to the empty set, then the probability of A united B is equal to the probability of A plus B, and this is equal to the probability of A plus the probability of B. So this is the additivity with respect to mutually exclusive events. As a consequence, the probability of an A bar, or not A, must be equal to 1 minus the probability of A, which is less or equal than 1. A bar is the complementary event. Moreover, the impossible event is the complementary of S, the sure set. So the probability of the empty set is equal to 0. Some remarks. A possible event is a subset of the sure event. The additivity of mutually exclusive event, so countable additivity, is necessary when the experiment has an infinite number of outcomes. There are two different views in probability, so the frequentist interpretation and the Bayesian interpretation. So for the frequentist interpretation, the probability of something corresponds to what fraction of the times it happens in the long run. And for the Bayesian interpretation, the probability of something corresponds to how likely we think it is to happen. The relative frequency concept, also known as measure of belief, is a non-rigorous way to introduce the concept of probability, which are widely used in engineering systems. For example, we can explain the probability of each face of a dice by means of empirical measures. Okay, let us consider the joint experiment of tossing a coin and extract a red card from a card deck. Each event can be decomposed in the following set. So C, which is equal to head, C bar, which is equal to tail, R, which is equal to the red card, and R bar, which is equal to black card. So the sure event can be decomposed in the following set. CR, C not R, not CR, not C not R. So for n experiment, we would have, for the relative frequency, f of something, so FCR is equal to n1 over n, FC not R is equal to n2 over n, F not C R is equal to n3 over n, and F not C not R is equal to n4 over n. From the empirical definition, the event head and red card is given by the relative frequency of C plus R, which is equal to the relative frequency of C plus R plus the relative frequency of C not R plus the relative frequency of not C R. And if we sum all the terms, we have that the relative frequency is equal to n1 plus n2 plus n3 over n. We can notice that we have head if either CR or C not R, and a red card if either CR or not CR. So we get that the relative frequency of C is equal to the relative frequency of CR plus the relative frequency of C not R, so it's n1 plus n2 over n, and the relative frequency of R is equal to the relative frequency of CR plus the relative frequency of not CR. And this is equal to n1 plus n3 over n. So if we substitute in the previous yield, we get that the relative frequency of C plus R is equal to n1 plus n2 plus n3 plus n1 minus n1 over n, so we add and subtract n1. And at the end, we get that the relative frequency is actually equal to the relative frequency of C plus the relative frequency of R plus minus the relative frequency of CR. So the same result that we have obtained using empirical relative frequency, we can derive it using the third axiom. So the set C is equal to the intersection of CR united with the intersection of C not R. The set R is equal to the intersection of CR united with the intersection of not C R. And C united R is equal the intersection of CR united the intersection of C not R united the intersection of not CR. We can notice that all are mutually exclusive, and hence we get that the probability of C united R is equal to the probability of C plus the probability of R minus the probability of C intersected R, which is the total probability law, where the probability of the intersection of C and R is the joint probability. The probability of an event can be affected by the a priori knowledge of some results of the experiment. So, for example, let us consider the probability of an event C knowing that the event R has already been verified. So, tossing the coin after that the red card is already been selected. Using the relative frequency, we have that f of C knowing R is equal to n1 over n1 plus n3. So if we multiply and divide by n, we get that it is equal to n1 over n times n over n1 plus n3. And this is equal to the relative frequency of CR over the relative frequency of R. In a similar way, we can define the relative frequency of R knowing C, which is equal to the relative frequency of C R over the relative frequency of C. If we use the axiom of probability, we can define the conditional probability. So the conditional probability is the probability of C knowing R is equal to the probability of the intersection of C and R over the probability of R. Indeed, we have that the probability of A knowing B satisfies the first axiom, since the probability of the intersection of A and B is greater or equal than 0, and the probability of B is greater than 0, since it already happened. The probability of the sure set knowing A is equal to the probability of A over the probability of A, and it is equal to 1, and it also satisfies the second axiom. And finally, if we have A1, A2, and so on, pairwise mutually exclusive events, one has that the probability of the union of A1, A2, and so on knowing B is equal to the probability of A1, union A2, union so on, intersected with B over the probability of B. And going on, this is equal to the probability of the intersection of A1 with B, union the intersection of A2 with B, and so on, over the probability of B. And we can separate those terms and have that this is equal to the probability of the intersection of A1 and B over probability of B plus the intersection of A2 with B over the probability of B, and so on. And this at the end will be equal to the probability of A1 knowing B plus the probability of A2 knowing B, and so on. And this satisfies the third axiom. In general, we have that the probability of A knowing B is equal to the probability of the intersection in AB over the probability of B. And one has that the probability of the intersection of A and B is equal to the probability of A knowing B times the probability of B, and it is also equal to the probability of B knowing A times the probability of A. As a consequence, if A and B are statistically independent, we get that the probability of the intersection of A and B is equal to the probability of A times the probability of B. Moreover, we can rewrite the probability of the intersection of A and B as the probability of A knowing B times the probability of B, which is also equal to the probability of B knowing A times the probability of A, in this form. So the probability of A knowing B is equal to the probability of B knowing A times the probability of A over the probability of B. If we generalize to n disjoint events, AI, where I is equal to 1 to n, we have that the probability of AI knowing B is equal to the probability of B knowing AI times the probability of AI over the probability of B. And it is also equal to the probability of B knowing AI times the probability of AI over the sum of j from 1 to n of the probability of B knowing AJ times the probability AJ. And this is the Bayes theorem. So we restate the Bayes theorem, and in this theorem we have different actors that plays a crucial role. So the probability of AI is the prior probability of I. So the probability that we know up front. We have that the probability of B knowing AI is the likelihood of B given AI. So it is how likely B happens when AI happens. And the probability of AI knowing B is the posterior probability of AI given B. So it is the probability of AI knowing that B has actually happened. And those are the basis of the Bayesian inference. So let us consider the Monty Hall problem, which is a show of the 70s, in which there were 3 doors. Behind one door there is $1 million, and behind the other 2 doors there is 2 goats. After our first choice, the game master opens one of the door with a goat behind. And in the actual TV show, the Monty Hall does this just for the pathos, but we will consider a version of this game of the statistician Steve Selvin. And so after the game master opens the doors with the goat, he will ask us to change the door, if we want to change the door. This problem by Steve Selvin can be interpreted in the light of Bayes' theorem. So if we define the door di with I equal to 1, 2, or 3, and we define the event the $1 million is behind door di with $I, and the event that Monty opens the door di as mi, we assume that we select the door d1, for example, and Monty opens the door number d2, and then he asks us if we want to change, so if we want to choose the door d3. Using the Bayes theorem, we want to compute what is the most convenient choice, so the highest between the probability of $1 knowing M2 and the probability of $3 knowing M2. So we have that the probability of $1 M2 knowing M2 is equal to the probability of M2 knowing $1 times the probability of $1 over the probability of M2. And the probability of $3 knowing M2 is equal to the probability of M2 knowing $3 times the probability of $3 over the probability of M2. For the prior, so our first choice, we have that the probability of $1 is equal to the probability of $2 is equal to the probability of $3, and it is equal to 1/3. Similarly, before Monty makes its move, and we select door D1, we have that the probability that Monty opens the door number 2 is equal to the probability of Monty opening the door number 3, and it is equal to 1/2, because we already chose the door number 1. We now make use of the likelihood, so the evidence that we can collect from Monty's choice. So our question is, what is the probability of Monty opening door number 2 knowing that the $1 million is behind door number 1? It's obvious that this probability is 1/2. In a similar way, what is the probability that Monty will open door number 2 knowing that the $1 million is behind door number 3? And it is 1. So at the end, if we compute the probability of $1 knowing M2, it is equal to 1/3, and the probability of $3 knowing M2 is equal to 2/3. So at the end, we should switch. We can notice that the probability of $2 knowing M2 is equal to 0, because it's an event that could not occur. Now let's enter into random variables. In the majority of engineering cases, the variables are not described by sets, but by number. So we define random variable as a real valued function that assumes a certain value according to the outcome of certain random experiment. So a random variable is not a conventional variable. For example, the number we got after rolling a dice is a variable, but the outcome we expect from the rolling is a random variable. So formally, random variable maps the set containing all possible outcomes of certain experiments. So the event space or sample space omega to the space of numbers. So if the mapping into one set is continuous, so for example the R set, the random variable is continuous. If the mapping is onto some discrete set, so for example the Z set, the random variable is discrete. In practice, for each small omega in capital omega, we get that x of omega is an element of the arriving set, so a number. And here we have a figure explaining that our set omega and our continuous set R. To be completely described, a random variable needs a probabilistic description that it is given in terms of probability density function, PDF. So, probability density function of a scalar random variable x at a certain value x equal to a is P of a is equal to the limit of delta a that goes to 0 of the probability of a minus delta a less than x less or equal than a over delta a, and this must be greater or equal than 0. We can notice the similarity with the ratio of increments of the approximation of the derivative. Since by the third axiom of probability we have that the probability of a less than x less or equal than b is equal to the integral of a from a to b of px dx, we have that the cumulative distribution function CDF of x at b is given by p of b is equal to the probability of x less or equal than b, and it is equal of the integral from minus infinity to b of px dx. In order to be a proper probability density function, we have that for the second axiom, we have that the probability of x less or equal than infinity, it is equal to the integral from minus infinity to infinity of px dx, and it must be equal to 1. We can also notice that the probability density function is actually the derivative of the cumulative density function in the variable. Moreover, we can state that the probability of a less than x less than or equal than a plus delta a, it is equal to the integral from a to a plus delta a of px dx. And for sufficiently small delta a, this means that we have that the probability of a less or equal than x less or equal than a plus delta a is equal to pa delta a plus o of delta a squared. So it is an Taylor expansion. And px represents the density of probability per unit value of a in the neighborhood of a. We can state that the p of x is greater or equal than 0 for all x from the first axiom. And furthermore, we can state that the probability of x equal to one value, a, is equal to 0. For the cumulative distribution function, we have that the probability of a lesser than x, less or equal than a plus delta a, is equal to the probability of a plus delta a minus the probability of a, which is verified by the p of a is equal to the probability of x less or equal than a, it is equal to the integral from minus infinity to a of px dx. The cumulative density function has the following properties. So the cumulative density function of a is greater than 0 and lower or equal than 1. The limit of a that goes to minus infinity of the cumulative density function of a is equal to 0, and the limit of a that going to plus infinity is equal to 1. The cumulative density function is a non-decreasing, and the cumulative density function is right continuous. So the limit of delta a going to 0 plus of p of a plus delta a is equal to p of a. Usually all the probability density function of continuous random variables have the following form. So px is equal to 1 over c n s times p of x minus l over c, where L is the location parameter, C is the scale parameter, and S is the shape parameter, and it is also the argument of the normalizing function NS. So if we have X distributed as a uniform distribution with parameter A and B, we have that the probability density function is given by Px is equal to a uniform distribution of X is equal to 1 over B minus A if X is in the interval AB and 0 otherwise. So the cumulative density function will be P of C is equal to 0 if C is less than A, C minus A over B minus A if C is in the interval AB, and 1 if C is greater than B. If we have that X is distributed as a normal distribution with the parameter L, C, and NS, so the Gaussian or normal random variable, we have that the probability density function is Px, and it is 1 over the square root of 2 pi times C times the exponential of minus x minus L squared over 2c squared, where ns is the square root of 2 pi, and it is the normalizing factor of the probability density function. So we have also the cumulative density function for the Gaussian distribution, and it is the integral from minus infinity to z of 1 over the square root of 2 pi times c times the integral of minus x minus L squared over 2c squared. We can do a change of variables and write it down as the integral from minus infinity to z minus L over c of 1 over the square root of 2 pi times the exponential of minus y squared in dy. And this integral is widely studied and is tabulated numerically. We can define the probability mass function for a discrete value random variable, and if you take the value in a set AI where I is a value from 1 to n, so we have that pi of AI is equal to the probability of x equal to AI, and it is equal to pi I, where pi I are the point masses. So in order to be a proper probability mass function, the sum of I going from 1 to n of pi I must be equal to 1. Using the property of the Dirac delta function, we have that the Dirac delta of x is equal to 0 for each x different than 0, and the integral from minus infinity to plus infinity of delta of x dx is equal to 1. So the probability density function corresponding to the probability mass function can be written as Px is equal to the sum of I going from 1 to n of pi I delta of x minus AI. We can notice that the previous relation holds whenever the probability density function is considered as a generalized function. If standard functions are used, the Lebesgue decomposition theorem should be considered. We can define also the cumulative probability mass function, so CPMF, as a staircase function. So the probability of x less or equal than a is equal to the sum of I going from 1 to n of pi I, 1 of a minus ai, where 1 of something is the unitary step function. We have an example here. We have a Poisson distributed random variable with rate lambda. The Poisson distribution describes the probability of a certain number of random points in an interval t. So the probability mass function is given by pi of a is equal to the probability of x equal to a, and it is equal to the exponential of minus lambda t times lambda t to the a over a factorial, where a is in the set n0. Sometimes we need to characterize a random variable with certain attributes, for example, the typical value or spread or variability. Those attributes are computed on the probability density function and not on the data. For example, we can be interested in finding the central value, so we can define mode. The mode is the value in which the probability density function attains its maximum value. So this is not a very good measure of the central value, since the probability density function we have could have multiple peaks. A good measure is instead given by the moment, which are concepts derived from the standard mechanics. So in general, we can define the earth moment for the discrete case around about the origin, so as mu r prime is equal to the sum over I of ai to the power of r pi I, and for the continuous case I has mu r prime is equal to the integral from minus infinity to plus infinity of x to the power of r p of x dx. We can also describe the Earth moment about the mean for the discrete case as CR prime is equal to the sum over I of AI minus mu 1 prime to the power of R times pi I, or in the continuous case as CR prime equal to the integral from minus infinity to plus infinity of x minus mu 1 prime to the power of R times P of x dx. So the Earth moment about the origin is called the Earth order raw statistical moment of a random variable. The Earth moment about the mean is called the Earth order central statistical moment of a random variable. More precisely, the moments are defined using expected value operator. So the expected value of x is defined as the integral from minus infinity to plus infinity of x px dx, or in the discrete case, the expected value of x is defined as the sum over I of AI pi I. Therefore, we have that the Earth moment for the row in the discrete case is equal to mu r prime equal to the expected value of x to the power of r, and in the continuous case is actually the same. And for the Earth central moment, in the discrete case, we will have that CR prime is equal to the expected value of x minus mu 1 prime to the power of r. And the same formulation is actually for the continuous case. We can notice that for r equal to 0 and mu 0 prime equal to 1 for each x, no information can be retrieved about x, and the same can be said for c0 prime. For r equal to 1 and mu 1 prime is equal to mu, so it's called the mean. It is actually the long run average. And for r1 equal to 1 and c1 prime equal to 0 for each x, no information can be retrieved about the x. And for r equal to 2 and c2 prime, defined as sigma squared, is called the variance. So if we summarize, we have that the moment for the mean case in the discrete, we have mu equal to the sum over I of AI pi I, and in the continuous case is mu equal to the integral from minus infinity to plus infinity of x px dx. And for the variance in the discrete case, we have that sigma square is equal to the sum over I of AI minus mu squared times pi I, and in the continuous case, we have that the variance is equal to the integral from minus infinity to plus infinity of x minus mu squared px dx. We can also define moments greater than the second order, and those are called skewness for the third moment and kurtosis or flatness for the fourth moment. Let us suppose that we have y equal to gx, where x is a random variable and gx is a certain function. We can define the expected value of y as the integral from minus infinity to plus infinity of gx p of x dx. We can further define the variance of x as the expected value of x minus mu squared, and it is equal to sigma squared. So we can also say that for the expected value, we know that if alpha is a deterministic value, the expected value of alpha is equal to alpha. And we can prove it by assuming that the deterministic value can be considered as a random variable with probability density function equal to the Dirac delta. Moreover, if we have alpha 1 and alpha 2, two deterministic value, and x1 and x2, two random variables, we have that the expected value of alpha 1 x1 plus alpha 2 x2 is equal to the alpha 1 times the expected value of x1 plus alpha 2, the expected value of x2. So we know that the expected value is a linear operator. So let's see some example of mean and variance for common probability density function. We have the uniform distribution, and the mean is equal to the expected value of x is equal to b plus a over 2, and the variance sigma square is equal to b minus a squared over 12. For the Gaussian is more complex. We have the expected value is the integral from minus infinity to plus infinity of x times 1 over the square root of 2 pi times c times the exponential of minus x minus l squared over 2c squared. And this can be decomposed doing some change of variables and splitting the integral into parts. At the end, after some not so complex passages, we will get that L is actually the mean. So L is the expected value. And it can also be done for the variance. So the variance is the expected value of x minus mu squared. And it is equal to the integral from minus infinity to plus infinity of x minus mu squared times the 1 over the square root of 2 pi times c times the exponential of minus x minus mu squared over 2c squared. This can be performed doing change of variables. And noticing that in the first integral we have this expression here, so this expression is equal to 1, and this expression will be equal to c. At the end, after some not so complex passages, we have that the variance is equal to c squared, and it is equal to sigma squared. We can also define sigma as the square root of sigma squared, and this will be called standard deviation. It has to be noted that only the first two moments are sufficient to characterize a Gaussian probability density function. We also have the example of the Poisson discrete random variable, so the mean, so the expected value of x, is equal to the integral from minus infinity to plus infinity of x times the sum of n from 0 to plus infinity of the exponential of minus lambda t times lambda t to the power of n over n factorial times the direct delta of x minus n in the x. After some not so complex computation, we can write down this formulation, and at the end we will get that the mean value is equal to lambda t. Interestingly, the variance of x for the Poisson random variable is equal to lambda t, so in this case the variance is actually equal to the mean. We can say that the mean value gives an idea of the central value of the random variable, while the variance gives an idea about the spread. Additional measures are given by the quantiles. So the quantiles are based on the fact that the cumulative density function is always invertible. So we can give the definition of quantile. So the art quantile is the value xr such that xr is equal to pr inverse. Usually quantiles are r equal to 0.25 and r equal to 0.75, and the difference 0.75 minus x 0.25 is the interquantile range. We can also define median as mu tilde, and it's actually the quantile for r equal to 1/2. In practice, in the discrete case, the median is the probability of x less or equal than mu tilde, and it is equal to the probability of x greater or equal than mu tilde. And in the continuous case is the integral from minus infinity to mu tilde of px dx, and it is actually equal to the integral from mu tilde to plus infinity of px dx. The median in general is a preferable measure of the mean and the variance for describing a probability density function, because this measure is less influenced by the tails and multimodal shape of a probability density function. And for this reason, the median is defined as a robust attribute of the probability density function. Let's see an example. Yesterday, 8 individuals paid this amount of euros to have a dinner in a certain restaurant. So 10, 10, 20, 360, 30, 10, 40, and 30. What is the typical amount of money you are expecting to pay for a dinner in this restaurant tonight? So if we compute the mean will be 60 euros. Then if we compute the mode will be 10 euros, because 10 is the most frequent event. But if we compute the median, it will be 25 euros. So which is the most appropriate measure? Obviously, it is the median. The median robustly replaces the mean, and the mean deviation replaces the variance. So mu bar is equal to the integral from minus infinity to plus infinity of the absolute value of x minus mu times px dx. Now here we can see some example some graph of the uniform distribution, the probability density function, and cumulative distribution function for the uniform distribution. So we see it's 0 outside, and it is a certain quantity in the middle. And here we have that the cumulative density function is going from 0 to 1 with a linear ramp. We can also see the Gaussian or normal probability density function as a classic shape of a Gaussian, and is a cumulative distribution function. And also we have an exponential continuous probability density function and cumulative density function. We also have a graph describing the Poisson discrete probability density function and cumulative distribution function, so a staircase function. So the lesson is over. I will leave you some references of this lesson.